marks a bend, a scalene cuts a corner, and a right angle provides the support to complete an exercise in art and aesthetics. And yet, in all this, the purpose of the furniture is never lost. The British critic and semanticist I.A. Richards claimed that art is a language, symbolic and emotive. In every piece of furniture here, the language of geometry expresses the emotion of utility with defining simplicity. The furniture reflects an eclectic symmetry with the medians and altitudes visible in every piece with great precision. These works ultimately awaken in us the memories of a whole range of theories on geometry associated with such great mathematicians as Pythagoras, Euclid, and Descartes. A straight line, as the Greeks believed, was the shortest distance between 2 points. This gave a ready reflection in planes generated on wood. The objective has always remained to cater to the principal need, utility through geometry. Geometry, a branch of mathematics, deals with the properties of space. In its most elementary form, geometry is concerned with such material problems as determining the areas and diameters of two-dimensional figures and the surface areas and volumes of solids. The designer has brought alive every feeling of the subject in his art. A home exhibiting such artifacts would be a tribute to an ancient art and at the same time retain the purpose of furnishing magnificently. One sees here a display of a unique blend of geometry which subsequently becomes the chemistry of bringing a change in the shape of wood through various designs. It is indeed a poetry of proportions, where the poet, the designer, has tried to convert every element of geometry into chemistry.
Good afternoon, friends. I, Rakhi Sharma, Program Coordinator ACPDM, welcome you all in this interactive teleconferencing sessions of Advanced Certificate in Power Distribution Management. In this session, we are going to discuss about the distribution lines. Now, I would request Mrs. Chandra to take up her presentation.
Welcome back, friends. We are going to discuss distribution lines. What are the equipment used in distribution lines? And the distribution lines can be of the following types. They can be overhead or underground. We had seen earlier differences. They can be radial, cross loop or loop network. The other classification is that the lines can be underground or overhead. Generally overhead lines are used, but underground cables are being used in some of the cities for improving the aesthetics. So we'll first take up the equipment used on the overhead lines. The main items for overhead lines are the supports, the insulators, the conductors, the cross arms and clamps of various types, the stay sets, the stay wire, the strain hardware sets, and the earthing sets. For example, we'll start with the supports. The pole or supports are classified as per the material used for the support. They can be made of steel, cement or wooden. We'll go first in the wooden poles. Earlier wooden poles were used quite substantially, but now we are moving on to concrete and steel tubular poles. But still wood poles are used at some places. The wood poles are chemically treated wood poles and are used for distribution lines. They were used because wooden poles were cheap. They were low in cost, but they are susceptible to decay. The wooden pole at the base gets corroded, and the specification of wood poles are covered by IS 876 and IS 5978. The timber suitable for poles is classified in 3 groups according to its strength: Group A, Group B and Group C. The Group A is very strong timber with modulus of rupture in bending above 850 kg per centimeter square, such as SAL. The Group B is strong timber with modulus of rupture 630 to 850 kg per centimeter square, and these are teak, siso, etc. And the Group C is moderately strong timber with modulus of rupture 450 to 630 kg per centimeter square, such as cheese, deodar, etc. They have further been classified according to the ultimate breaking load into 7 classes, like class 1, class 2, class 3, 4, 5, 6 and 7, and the ultimate breaking loads for these are indicated. Class 1 has 1350 kg, class 2 1100 to 1350 kg, class 3 850 to 1100 kg and so on. Then we have the concrete poles. These are more expensive than wooden poles but cheaper than the steel poles. They are used extensively for power distribution in urban areas and in remote and inaccessible places, as concrete poles can be manufactured at the site itself. They are also preferred where decorative considerations predominate. These concrete poles can be of 3 types. They can be precast cement concrete poles, reinforced cement concrete poles and pre-stressed cement concrete poles. The PCC poles are made of cement concrete, and cement concrete is an artificial product obtained by hardening of the mixture of cement, sand, gravel and water in predetermined proportions. The low maintenance, competitive price and aesthetic appearance of precast concrete poles makes them superior to steel or wood for use in electric lines, and the ease and speed of installation means faster project completion and lower installed cost. Then we have the RCC poles. Plain concrete can withstand very high compressive loads, but it is very weak in resisting tensile loads. Steel, on the other hand, can resist very high tensile force. Hence, steel is embedded in concrete wherever the tensile stresses are expected in concrete. Such a concrete embedded with steel is called reinforced cement concrete pole. The RCC poles have an extremely long life and need little maintenance, but they are bulky in size and comparatively heavy. They have shattering tendency when hit by a vehicle. The reinforcing bars and wires used for the manufacture of reinforced concrete poles are mild steel and medium tensile steel bars, and hard drawn wire conforming to IS 432, and annealed wires with an ultimate tensile strength not less than 32 kg per square mm. Then we have the pre-stressed concrete, cement concrete poles. They are known as PSC or PSCC poles. These PSC poles take care of the shortcomings to some limit. However, the handling, transportation and direction of these poles is more difficult because of their heavy weight. The pre-stressed cement concrete pole is manufactured by placing pre-stressed steel strands and spiral reinforcement in a mold and adding fresh concrete and spinning the mold to form the pole. Then we have poles of the steel type. The principal types of steel poles used are the steel tubular pole, the rail pole or the RS joist, the fabricated tower and the I-type beam. The specifications for steel tubular pole are covered in IS 2713, and due to their light weight, high strength to weight ratio and long life, they possess distinct advantages over other types of poles. These are of two types, stepped and swagged. Step poles are manufactured from a single tube, the diameter being reduced in parallel steps by passing the tube through a series of dies. The use of a pole cap at the top and concrete muff in the ground and regular coating prolongs their life. Then old and rail and RS joists. Old and second-hand rails and RS joists are frequently used as supports for overhead lines. The portion embedded in the ground is covered by concrete muff and the remaining portion by regular paint unless galvanized steel is used. And a suitable pad of cement, concrete, stone or steel has to be provided at the bottom of the pit before the metallic pole is erected. Where metal works are likely to get corroded, a cement concrete muff 20 cm above and 20 cm below the ground with sloping top is provided. The working load of rail and steel joists I have indicated. These are the various types of rails which are available. For example, rail 29.74 kg per meter or rail 37.17 kg per meter. These are various rails which are available. The lengths of 9 and 11 are used and their working loads are also given in this slide. Then we have the fabricated or lattice type supports. These are fabricated from narrow base steel structures. They are light in weight and can be assembled at site if bolted construction is used. Normally both welded and bolted types are used, and the portion embedded in the ground should be protected by concrete muff and the remaining portion by regular paint unless galvanized steel is used. Then the size and height of the pole depends upon the span length used. We have different span lengths for LT 11 kV and 33 kV. The conductor size and tension, the voltage level, the phase and ground clearances, the forces acting on the pole, self weight, the weight of conductor, the ice, the wind pressure on the pole, the cross arms and conductors, and the planting depth. Varies from 1/6 to 1/10 of pole height, usually between 1500 centimeter to 1800 centimeter. That is how we select the size and height of the pole. Then the next item which is used for power lines is an electrical are insulators. As we know, the electrical insulator resists the flow of electricity, and application of voltage difference across a good insulator results in negligible electrical current. Insulators keep the electrical current from energizing the power pole. They are basically used to prevent the electrical current from energizing the power pole. The various types of insulators which are used in connection with overhead lines are the shackle insulators, the pin type insulators, the suspension type insulators, and the guy strain insulators. We will go into each of these insulators. The shackle insulators are used for 400 and 230 volt lines for tension as well as tangent locations. Shackle insulators are used for distribution lines, dead ending and supporting conductors laid in vertical formation. This is the example of a shackle insulator. The picture is not very clear, but this is how it looks. Then these shackle insulators are according to IS 1445, which covers insulators for voltages below 1000 volts. And the two standard sizes listed in the specification are 90 mm dia and 75 mm height, and 115 mm dia and 100 mm height. And a shackle insulator supported by either two straps and 2 ms bolts, or one U clamp or D strap and 2 ms bolts is used. Then we have the pin insulators, most commonly used. These are manufactured for voltages up to 33 kV and are cheaper than the other types. IS 1445 and 731 cover the detailed specifications for these insulators, and their typical dimensions are as indicated in the slide. For 11 kV, maximum diameter is 152 mm and height is 137 mm. For 22 kV, the maximum diameter is 210 mm and height is 195 mm. Then 33 kV, the maximum diameter is 278 mm and the height is 242 mm. This is the example of a pin insulator for 33 kV. This is a pin type insulator for 11 kV. Then we have the suspension insulators. The cost of a pin insulator increases very rapidly as the working voltage is increased. For higher voltages, this type is uneconomical, and there is further disadvantage that replacements are expensive. For these reasons, high voltage lines are insulated by means of suspension insulators, in which the line conductor is suspended below the point of support by means of the insulator or insulators. It consists of this, and the disc of the suspension insulator consists of a single disc-shaped piece of porcelain grooved on the undersurface to increase the surface leakage path, and to a metal cap at the top and to a metal pin underneath. We can see this. This is a disc of the suspension insulator. Again, this is the disc of a suspension insulator. The disc insulators are made of glazed porcelain or tough glass. The specifications for disc insulators are covered in IS 731, and their dimensions have been standardized in IS 3188. Each insulator is designed for a comparatively low working voltage, usually about 11 kV, and the insulation for any required line voltage can be obtained by using a string of a suitable number of such insulators. 3 numbers for 33 kV in series and 1 number for 11 kV. So the 11 kV insulator will consist of 1 disc, and the 33 kV insulator will consist of 3 discs. In the event of a failure of an insulator, 1 unit instead of the whole string has to be replaced. Whereas in the case of the pin insulator, the entire pin insulator has to be replaced. So this is the advantage of a disc insulator. You can see this is an 11 kV disc insulator. The disc insulators are of 2 types, the ball and socket coupling type and the clevis and tongue coupling type. Both connection types are commonly used, and suspension insulators are also known as disc insulators, as I said. So the dimensions of the disc insulators for the ball and socket coupling are like type 1, they are classified as type 1 and type 2, and the nominal dia is 255 and 280, and nominal spacing is 1.
There is a caller from Maharashtra. Yes, please ask your question. Yes, Maharashtra, please ask your question.
I want to know about this vibration dampers used on overhead lines.
Pardon?
Vibration dampers are used in...
yes, so that these do not vibrate, the lines do not vibrate. They are usually used on high voltage lines. They are not used on LT or 11 kV lines. The vibration dampers are used on the high voltage lines, higher voltage, EHV and above. So the suspension insulators in the tongue and clevis type, a round pin with quarter pin is used to hold the tongue of one unit in the clevis of the other. And in the case of ball and socket type, the insulators are assembled by sliding the ball of one insulator into the socket of the next insulator. This is a tongue and clevis type of insulator. You can see there is a tongue and there is a clevis. This is a tongue and clevis type insulator shown. Then we have the guy strain insulators. Egg-type porcelain strain insulators are used for insulating stay wires, guard wires, wherever it is not proposed to earth them. The insulator is fixed between the guy wire almost in the middle. The bottom portion of the guy wire gets insulated, and any human being or animal coming in contact with the bottom portion will be safe. Basically, the idea of the guy strain insulator is to keep the bottom portion insulated from the pole, so that any human being or animal coming in contact with the bottom portion of the stay wire will be safe. The guy strain insulators are of two types, A and C type. A type is for the 400 and 230 volt lines, and the C type is for 11 kV lines. As per IS 5300, two strength sizes are used, 44 kilonewton for A type and 88 kilonewton for C type. This is the example of a guy strain insulator. You can see this, it can be egg-shaped or this type of strain insulator. Then the next item used is a strain hardware set. The conductor is strung between sections through a strain hardware set. It is fixed with the disc insulator. If 3 discs are used for 33 kV, then it is fixed at the end of the last disc. It is made from malleable iron or aluminium alloy, and set with aluminium alloy is preferred to keep losses minimum. We then have the stay sets. Guys of standard galvanized steel are used on all terminals, angle and other such poles where the conductors have a tendency to pull the pole away from its true vertical position. Generally, we see that the poles tilt away from its normal vertical position. To keep them in place, these stay sets are provided. Transverse guys perpendicular to the direction of overhead lines are used when the poles are located in sandy and waterlogged soils of low cohesive strength. The guys are fastened to the pole near the load center point with the help of pole clamps. The other end of the guy is secured to a stay rod embedded in the ground. MS or galvanized steel is used for stay sets. The stay rod is located as far away as possible. You can see this is the figure of how stay is provided. You can see the pole, how it is held in vertical position by the stay set. And you can also see the guy strain insulator or stay insulator at the middle of the stay. So this is how the stay set is installed. Then we have the cross arms. They can be made of wood or fiberglass or iron, and steel cross arms are stronger and last much longer. MS angle iron and channel iron sections are also being used for this purpose, and the shape and length of cross arms depends upon the desired configuration of conductors, whether we are using vertical, delta or horizontal configuration. V cross arms are used for tangent locations with clamps, double channel cross arms for tension or cut point locations where double poles are used. Then we have the earthing knob. The earthing knob is used for supporting the neutral cum earth wire used for earthing of metal parts of supporting structures of low tension lines. The knob is generally made of cast iron and 52 into 42 mm, and its electrical resistance is not to exceed 200 mega ohms. The breaking strength at the neck of the knob is not to be less than 11,500 kg when force is applied. Then we have the conductors, that is the main part of the line. And the conductor, as we also talked about earlier, is that which allows the flow of electricity. It is through the conductor that all the supporting equipment is for the conductor. And these conductors may be of copper or aluminium, these materials are the conductor of choice because of their non-magnetic characteristics and their low resistivity. And we talked about conductors like we have all aluminium conductor, triple AC conductor, and the ACSR conductor in the morning session. Then we have the earth sets. Two types of earthing arrangements with GI wires are used. 8 SWG GI wire is used with 115 turns, which are closely wound, and winding die is 50 mm and length is 1500 mm. Or we could also have with GI pipe. GI pipe is used as 40 mm dia and 2500 mm long. These are used for earthing the poles. And the recommended spacing of ACSR conductors is given in IS also. This is some of the recommended spacing which I have indicated for 11 kV and 33 kV for 60 meter span and 90 meter span. But this is also given in the IS as well as the IE rules. Then we have the insulator ties or binding tape. The binding tape is used for binding the pin insulator, shackle or line insulator to the conductor. The tape is wound on the conductor. The metal of the binding tape should be same as that of the conductor. Otherwise there will be bimetallic reaction. So therefore the metal of binding tape is used as the same as that of the conductor. And the first layer is wound along the wire in direction of twist of wire, and second layer is in opposition to the twist. The portion on which the binding wire is to be wound should be taped 25 mm more from either side. This tape is used for avoiding conductor snapping due to friction. Otherwise, when the insulator is put on the conductor, then there will be friction. Then danger boards are also provided on the lines, and danger board should be fixed on every HT pole at following points. Danger board of every roadside pole should face the road. Danger board should be on both side poles at road crossing, telephone crossing, power line, railway and river crossing, and up to half kilometer on both sides of village or city. Then we have guarding. Guarding means safeguard, as we all know. So this is below the line. In case of conductor snapping, it will touch the guarding wire before laying on ground or will lay on the guarding. The guarding is always earthed, and the line protection will operate and switch off the line. The basic idea is that once the conductor snaps, then the conductor will fall on the guarding and the line protection will get operated. The snap conductor will not remain charged. If it falls direct to the ground, then the snapped conductor will remain charged, and this will cause accidents. Hence, guarding of especially the 11 kV and 33 kV lines is very important. That is why guard wires are provided. The guard wires are to be used at all points where a line crosses a street, road or railway line and other power lines or telecommunication lines. As per IE Rule 88, guard wires of galvanized steel of minimum 4 mm dia having breaking strength not less than 635 kg should be used. Should be fitted on structures on either side of the crossing. Guard wires should fully cover the phase wires and accordingly should not be more than 30 cm away from the outer phase wires. The other line accessories which are used are spool ties, T-connectors, lashing rods and line guards and preformed fittings. There are other dead-end fittings like LT conductor dead-end grips, guy grips, service grips, full tension splices, distribution ties, side ties, which you all see when constructing a feeder or a line. Then the joints. Joint formation is very important because the losses in joints are very high, and if the joint is not properly made, it has been observed that the losses in the joints could be as high as 2 to 3% of the total losses. Therefore, the joint should conform to IE rule 75. For conductors up to 50 mm square, crimped joints are made with simple hand crimping tools. For higher sizes, compression type or hydraulic type crimping tools are used. Up to 50 mm square, we can make them with hand and other simple hand crimping tools, but for higher sizes, compression type or hydraulic type crimping tools should be used. The joints can be of various types: uni joints, compression joints, twisting joints, two-part compression joints, and dead-end joints. Then we use the LT line spacers. You must have seen sometimes wooden spacers or otherwise also. So these spacers are used to prevent clashing of LT conductors in the mid-span due to sag, wind, and longer spans. This could result in faults and interruptions, and therefore spacers are provided to overcome this problem. You may have seen these spacers if you look at an LT line on the road. So how is an overhead? What are the factors considered for design of an overhead line? An overhead line is normally designed keeping in view the electrical and mechanical requirements. The electrical design involves selection of voltage, selection of conductor, voltage control, and selection of the protective control gear. The mechanical design involves stress and sag calculations and the design of supports and cross arms. The supports must be strong enough to withstand wind, loads acting on the supports, conductors, insulators, and cross arms, etc. And as for the routing of the overhead line, for single and edge pole lines, easy accessibility for patrolling and maintenance work determines the layout. That is, they are laid as near to the roads as possible. Maybe in rural areas this may not be possible, but we try to keep the lines as near to the roads as possible so that we can patrol them and find out when there is a fault on any section. Then we have completed the overhead material used on overhead lines. We'll go to the underground cables. These are also being used at 11 kV and LT, and sometimes at 33 kV. They are very expensive as compared to the overhead lines, but still they are being used. They are sometimes preferred due to eliminate outages by abnormal weather conditions such as snow, rainstorms, lightning fires, trees, accidents, etc. So if we want to increase the reliability, we use underground cables. Then this system is more aesthetic. The overhead lines are not very aesthetic. They are on the roadside, but if we use underground cables, then we cannot see them. Then the right of way for erecting overhead systems is no longer available. Then also we use underground cables, and it is possible to extend the supply from source to load center on any route profile. Overhead lines are generally to be taken on the on the sides of the roads, but this can be extended on any route profile, and fairly uninterrupted and reliable power supply can be maintained through underground cables.
So friends, this is the interactive session. You can ask any question at any time. Our toll-free number is 18001 12345. I am just repeating the toll-free number 18001 12345. And other studio numbers are 011 2953 2845. I request to ask any question. If you have any doubt, you can ask any question at any time during the presentation. I also request from the coordinators of the various study center and the regional centers, please send the attendance of the students by fax. Thank you.
So we were talking about underground cables, and fairly uninterrupted and reliable power supply can be maintained through underground cables. And you can see this is a picture of the underground cables which are being used. They can be of various types, and the selection of cable, the factors which influence the selection of the cable is the load, the system voltage, the type of insulation, the short circuit reading, the mode of installation, and economy and safety. For the same conductor size, the maximum continuous current carrying capacity depends on the depth of laying, ground temperature, ambient temperature, and proximity of other cables and types of ducts used and load cycle.
Yeah, there is a call from Karnataka. Yes, please ask your question. I think the call has disconnected. You may call again. Okay, we may proceed.
Yes, okay. For example, we have three types of cables: the PILC cable, which is called the paper insulated lead covered. We have the PVC cable, and we have the XLPE cable, which is the cross-linked polymer cable. So we at
Yes, please ask your question. Yes, Karnataka, please ask
Hello,
your
madam.
question. Yes.
Hello.
Yeah.
hello, yes.
Hello.
Yeah, we are listening. Please ask your
Oh.
question.
Hello.
Okay, you may ask again. So we may proceed. Yeah.
Well, we were talking about the maximum permissible conductor temperature for various voltages and for various types of cables. This slide indicates what are the permissible conductor temperatures for various cables. So, depending upon the voltage at which the power is transmitted. Yes.
Yes, Karnataka, please ask your question. Yes, ask your question.
We are not able to hear you.
Yes, Karnataka.
Hello.
Yes, ask. Please ask.
Hello.
Hello, please ask your question.
Hello. Madam, why we are putting only these values as
Pardon?
220 kV, 33 kV, 11 kV? Only we have putting only these values. Why? The reason is what, madam?
Pardon?
What is the reason why we have putting only
Because
these
this
values?
is a course on power distribution. We are taking the voltages of sub-transmission and distribution. We are not taking the transmission system. This is the course on power distribution
No,
systems.
he's asking that we are taking only 11 kV, 22 kV like this, these figures.
Yeah.
Why we are taking this kind of figures?
These are the voltages which have been chosen by our country. In other countries, they do have 6.6 kV also. The higher, you can choose any set of voltages, but once you choose a set of voltages, your entire system is designed for that voltage. For example, in a disc insulator, we have taken 11 kVs and we put 3 discs for 33 kV. So you have to choose some voltage. You have to choose any voltage. So the equipment is designed for that voltage. In America, we have equipment designed for 110 volts. Whereas in our country, we have chosen the British system because we were dominated by the British for a very large time. And we followed what was in the European practice or the British practice. So whatever they were following in the beginning, we also adopted those systems. These are the voltages which were adopted by the British system. So we are adopting those systems. Had we adopted American practice, then we would have gone in for 110 volt at the consumer end and corresponding voltages.
And all
at
the
higher
system
end.
and all further system is designed on the basis of this
These.
voltages only.
So this is the British practice which we are following.
Just like frequency, somewhere
Yeah,
50
somewhere
hertz.
it is 50, somewhere it is 60 hertz. The American practice 60 hertz, whereas the British and Europe practices 50 hertz. So it depends on the system which you have taken in the beginning, then you have to keep on following that same system. And usually we have phased out voltages which are non-standard. For example, we had 6.6 kV at a large number of places. Most of the PHE systems were at 6.6 kV. But now we are telling them to move to 11 kV because if we have non-standard voltages, then we will have to have many sets of equipment, larger inventory, and the losses at 6.6 kV will be higher than at 11 kV. So we are moving towards 11 kV. Even in distribution, we are moving from, say, 400 volt to 11 kV. So the idea is, once you have chosen a set of voltages, then it is very difficult to change because then you have to change the entire equipment. For example, if you have a transformer of 33 by 11, it may be difficult to change from 33 to 33 by 12, or you will have to have a 2-winding transformer in between. So once the idea was following the British practice. Whatever was followed in Britain, we were ruled by the British when electricity came to India, so we have followed the British practice. We have not followed the American practice. That is why we have chosen these voltages.
The system is so costly. Overall change will be
it cannot be changed very easily.
Yeah.
Because once you put in a system, it is very difficult to move to another voltage.
Okay, I think you have got your answer. So
somewhere it is like in Maharashtra it is 22 kV, whereas in Punjab it is 66 kV, and in most of the other states it is 33 kV. So there are differences, but generally they are in the ratio of 11, 30, 22, 66, 110, 132. So that is the reason. I hope you have, your question is answered. So we were talking about cables. Selection of the cable. The initial cost of laying the underground system is very high, but the maintenance charges.
Still, you have any doubt, you can mail to our expert. And
yeah, I'll tell you my mail address.
Yes, write the mail ID of your expert. You can mail her, and maybe your query maybe clarify.
Yeah, it is ANJULI_CEA@yahoo.co.in. I'll repeat my mail address. It is ANJULI_CEA@yahoo.co.in. You can ask any question, but main reason was the adoption of the British system at the time of, when electricity started in the country. And when you adopt one system, it is difficult to go to another system. The underground system is, almost 10 times costlier than the overhead system. So you have to be, that is why the underground systems in our country are not very prevalent, because we are not that rich a country, but they are in use in our country. The sizing of the cable depends upon its current carrying capacity, the short circuit current, the voltage drop, and the losses. We have to keep the voltage drop, like the overhead conductor, we have to keep the voltage drop at the consumer premises within the limits, that is plus minus 6%. Even at 11 kV and 33 kV, the voltage limits are prescribed. So the sizing of the cable will depend on the voltage regulation which we want to achieve, its current carrying capacity, its short circuit current, and the losses. Then the cables jointings and terminations in case of cables are very important. The cables are supplied in reels of standard lengths, and joints have to be made, and all joints are to be made as straight through joints, so that each joint has the same features and characteristics of the original cable. Straight through joints and end terminations are costly, and they need skilled staff. They shall provide core continuity, stress controlling screens, insulation, earth lead, mechanical protection, and protective covers. So special lugs have to be used at terminations, and we have various types of joints and terminations. Earlier we were using cast iron molded joints and terminations, which are now obsolete. The new types are the epoxy resin type, the heat shrinkable type, the cold shrinkable, and push-on type. And these cold shrinkable, you have to hardly do anything, and the push-on type also, they get clamped to the cable in the cold or ambient temperature conditions. These are the various terminations. You can see this is one type of termination which I have shown. Then this is another type of termination which can be used. Then we have the aerial bunch cables. Aerial bunch cable is a cross between the overhead and the underground cable. So the aerial bunch cable is a cable which can be used above the ground, and it is used in place of overhead lines to prevent theft by the consumers. You cannot hook overhead cables, because in overhead lines they are bare conductor. You can hook the bare conductors, but aerial bunched cables, it will be difficult to remove the insulation. Therefore, now at 11 kV and LT, especially in the high voltage distribution system, aerial bunched cables are being used, and these aerial bunched cables are extensively used in Delhi. For example, you can see them with the high voltage distribution system along with small distribution transformers, and the aerial bunched cables are in cost between the overhead line and the underground cable. They are about 2 to 3 times more costly than the overhead line, but they are about 5 to 7 times cheaper than the underground cables. That is why utilities are preferring to go in for aerial bunched cables. When you install underground cables, you have to dig the road, and you should be very sure where the underground cables are placed, because fault location in a cable, you must know exactly where the cables are placed. But in an aerial bunched cable, they can be taken on ordinary poles, they can be taken along the wall of a building. That is the advantage. They can be taken on ordinary communication poles. We can use aerial bunched cables in place of overhead lines. So the 3 types of things we are using is the overhead line with bare conductor, the overhead aerial bunched cables, and the underground cables. And to prevent theft on overhead lines, now the overhead line bare conductor is being insulated with some insulating paint, but experience of the utilities has shown that even with this insulation paint, the paint is scraped off and people resort to hooking. So to prevent this, some of the utilities are now using some sheath over the overhead lines to prevent hooking.
So friends, you have enlightened us on the various aspects of the power distribution system, distribution and this equipment, substation equipment and distribution line. I express my sincere gratitude to Mrs. Chandra, and I express my sincere thanks to all the learners and the viewers of this program. There is an announcement. The next teleconferencing session is on 6th of April, where you will study about the energy management and IT applications. We will have the expert from the utility, and thanks, and have a good day.